All right. So let me get my computer situated here. Okay. So I was thinking this title is slightly inaccurate. Managing, I guess, kind of describes what I'm going to talk about today, but I'm going to provide quite a few different kind of examples of how these stations are being used so that folks can get an idea of, what you can do with them, from that perspective. So that is, I guess, in a way, managing. But I'm also going to then talk about just how you actually physically manage the stations, cleaning sensors and using Monitor My Watershed to check the data and to do some quality control checks and stuff like that. So here we go. Okay, so our main goal for today is to just understand ways that you can use these stations and then simply how to keep them functioning and collecting good data. So I'm going to, as I mentioned, I'm going to talk about examples of how to use these stations. And then I'm going to go through some management approaches, including maintenance, cleaning sensors and such, doing quality control, and doing some troubleshooting. And I think we're having some non-muting going on. So if folks could just mute, I'm getting some feedback there. And then George is going to do a case study after me. So the types of work that is being done with these stations, it's a wide variety of usages. It's really dependent on your particular situation and what you want to do with the available data that can be collected using these stations. So anywhere from working with municipalities on local issues to dealing with flooding issues. Salt is certainly a prominent issue these days, freshwater salinization syndrome. General pollution assessment, looking for unwarranted discharges, et cetera. Looking into trout habitat temperature, obviously a big issue with trout. Agricultural restoration and associated sediment inputs. And then quite a few schools working with these stations in their classroom and lab work. So there are a few county conservation district folks that are working with these stations currently. I have an example of some of the data that Kent has been collecting in the Manor Creek watershed. Cheryl, of course, spoke yesterday about her work. Scott's got a station there in Fulton County, and then Emily up in Potter County has a station as well. So I'm first going to go through some common data patterns that we see, just very generally kind of standard data patterns, to give everyone a feel for just the basic trends we're seeing. So seasonal and daily temperature fluctuations. There's an inverse relationship between depth and conductivity during storms. That's a dilution of stream water with stormwater. Certainly conductivity spikes are common in the winter, especially in urban areas due to road salt and de-icers. Conductivity increases due to unknown sources. Certainly just a kind of a scanning approach to looking for discharges, illegal discharges. And then certainly turbidity increases during storms. So here's our sort of temperature patterns that we see: seasonal changes, winter, summer, so on, and then daily fluctuations. Here's the dilution pattern I was talking about with regard to conductivity. So you can see a base flow conductivity here of between 6 and 800, which is pretty high. This is a station in the Philly area, Nailers Run. It's an urban watershed, and you can see with each depth increase, there's a decrease in conductivity. Stormwater is generally lower in conductivity, lower concentration of ions than stream water, higher ion concentration, higher conductivity. So you can see extreme dilution with these severe kind of flashy flows coming in from urban runoff, very quick kind of pulses of large amounts of water coming in here and diluting stream water almost down to practically almost to zero, not quite zero, but below 100. So really showing how flows are affecting kind of in-stream conditions. And this dilution can almost be seen as a indicator of wacky hydrology, because the more extreme the dilution, the more that's going to indicate severe kind of flooding potential and just flashy flows in general. And then spikes in conductivity due to road salt. This is a common pattern, as I mentioned, in urban areas. So you can see here, any little increase in depth is associated with conductivity spikes. Now, these increases in depth are associated with with winter weather, certainly, with salt being applied to snow and ice, and then that melting and flushing into these streams and giving these spikes in conductivity. And I'll mention some examples later, but these ranges are way above normal and certainly presenting toxic conditions to biota in the streams. Also, just keeping an eye out for and seeing random increases in conductivity. These can be actual pollutants. It can also be fouling or sensor malfunction. So this is sort of speaks to the fact that you need to have a quality control process for confirming patterns that you're seeing in the data, whether those patterns are actually real or not. This is in a forested stream, heavily forested stream in this First State National Historic Park. And this kind of looked real, but then you get some weird patterns here. And we actually ended up confirming that this was actually just a sensor fouling issue, I believe it was. And then turbidity increases. As we all know, when storms come in most areas, any area that isn't heavily forested, pretty much, especially agricultural areas, are going to show increases in turbidity with depth. So we see depth here in blue, turbidity in green. You can see a really close correlation between as depth increases, turbidity increases. This is more of an urban watershed, and yet we still see turbidity increasing. Agricultural watersheds, you may see even more extreme increases in turbidity. So now I'm going to go through some examples of usage. This is kind of a detailed list here. I'm hoping to get through most of these. We'll see how far we get. So I mentioned First State National Historic Park. This is the Delaware the Nature Conservancy in Delaware. They're stream stewards doing this work, looking at water quality of streams entering the national park. Some master watershed stewards have done some work on Pickering Creek, and I have a case study of some kind of pattern inputs that were happening and that were seen in the conductivity data that they tried to sleuth. And then stormwater and urbanization, Darren Brake with Darby Creek Valley Association, working on a watershed there to deal with flooding issues. Agricultural restoration and sediment, again, some of the work that Kent is doing there on Manor Creek. And then some examples of how these stations are being used in some classroom work. And then some more urban study going on in Westchester. Patty Haug, who was a student, graduate student at Westchester and a master watershed steward working along with George Seeds and a local high school student as well, doing some investigations on salt chloride measurements. And then a watershed management study we did, watershed characterization we did in collaboration with the Wallkill Watershed Management Group on the Pollins Kill in northern New Jersey. It was kind of a detailed study that provided recommendations based on the data. So I'm going to go through these. So here's the stations that have been deployed in the First State National Historic Park. So you can see their locations here within the park, all kind of tracking water as it comes into the park. This is the stream stewards with the Nature Conservancy. They manage these stations and have done some additional work going upstream of these stations to look at causes of the pollution that is being seen. So this is a real example here. Some of these stations coming off of heavily developed mall areas and such, and seeing conductivity spikes. This isn't even the maximum that we've seen. We've seen above 50,000 microsiemens per centimeter in the wintertime from these stations. This is large amounts of salt and de-icer flushing in from large parking lots, and getting the stream water to a point where it is flowing as salty as seawater. So that certainly, those types of short spikes are going to be toxic to invertebrates, amphibians, et cetera. But there's also kind of this base flow conductivity level, which you can't see here, but I'll talk about in some of these other examples, where the groundwater is being contaminated. And that really is more of an ongoing, possibly even more severe issue. So the stewards, with regard to that base flow conductivity, you can see here at base flow, when the conductivity isn't being diluted in summertime, you can see that conductivity is running between 700 and 900 microsiemens per centimeter. Generally, natural levels are between 1 and 200 in this region. So these are contaminated streams. And what they did is they went upstream and measured at all these different pipes and inputs coming in from this mall area here. Here's the station, and they went upstream and measured at all of these different inputs. These are pipes and little small tributaries coming in off of all of this impervious surface, measuring with a handheld meter. And they were able to identify some really hot spots and have been working with the mall and with the county to address some of these inputs. And again, I think we're getting some unmuted people. So if you could just make sure you're muted. So moving on, in Pickering Creek in southeastern PA, there was this kind of patterned spikes in conductivity. You can see this regular patterning. And so that was really totally unknown, whether it's a regulated, unregulated discharge of some material, who knows what it was, but you can see it was causing substantial increases in conductivity. So the baseline conductivity between 250 and 300, causing it, these spikes were causing it to go up to 500 to 550. So Carol Armstrong, a master watershed steward in Chester County, along with some others, I think George may have been involved with that, went out and tried to time it so that they were measuring upstream at likely sources with a handheld meter to try to identify where these increases were coming from. But it's kind of hard to pattern that, because you've got multiple potential areas to look at, and you have to time it according to the data. And I think at this time there was some cell transmission issues too. So if you can't read it live, then that makes it even harder. So that's points to the benefit of having totally live data, is you can time your field work accordingly and try to sleuth out issues like this. So the pattern kind of quickly disappeared without them being able to identify where it was coming from. And then it reappeared briefly in November and has disappeared entirely. So you can see all of these points here that are non-winter associated. This is winter, but you can see all these increases here in conductivity in non-winter months kind of disappeared in here, few in here, and then kind of have disappeared since then. So that question remains unanswered, but kind of speaks to sort of some of the issues that can happen and how you might go about trying to figure out what's happening. but that was enough of an increase in conductivity that really could have been an important issue affecting the stream. So moving on to stormwater and urbanization, this is work that Darren LeBrake with the Darby Creek Valley Association has been doing. This is the watershed. Here's the station here, delineated upstream of the station. This stream network is actually all piped. So this is what it should look like, but this network has been entirely piped. So it's all pipes upstream of here. Darren is working with this neighborhood to develop green stormwater infrastructure and possibly even daylight the stream. But you can see here, this is a small stream, and you can see here that pretty much any storm that comes through causes pretty major increases in in stream depth. So this is an issue with flooding and just generally with stream dynamics. There's also severe salt issues here, as well as all of the other contaminants that sort of are correlated with salt. So salt is not only a stressor itself, but it's an indicator of lots of other urban contaminants. So Darren also installed a video camera to be triggered during these storms. So here you can see base flow. And this is one of those 1 to 2 meter storms coming through here. You can see that it comes over the bank and floods this entire golf course. He is working with this golf course to do riparian buffers in here, but a lot of the issue is upstream of the golf course. So that's certainly a way you can use these stations to investigate and start moving towards dealing with flooding and stormwater hydrology issues. This is an interesting graph that Darren developed from his other station on a tributary to the Schuylkill near Birdsboro. And what it shows here, it's a little detailed, and I hope folks can see it, but this is during Ida, the recent hurricane. So you can see here, this level is sort of what Darren predicted would be a normal 2-inch storm. So you can see how dramatic this storm went. This is a tiny stream, and yet it's in a kind of a channel that has been cut, and it went up to over 12 feet high for an extended period of time. But you can see here some interesting, this speaks more to just how these stations function and what the data can tell you. But here you can see this in this what Darren calls a curve deflection, where the stream went out over the banks. So this is the point. You can see there's a transition where the depth didn't go up as quickly after it went out over the banks. And then it comes up here. Here's where it hit the bottom of the waterproof case of the logger station, of the monitoring station. Here's where he noticed that there was no more charging going on because the solar panel got covered. And then here's where he noticed that the station stopped transmitting entirely when the entire box was covered by water. So the data kept being collected to the SD card, but this is the point where it stopped being transmitted to monitor my watershed. So he plotted these data from the SD card and showed this point where data stopped transmitting from the station because of the entire station being covered in water. And so you can see that that waterproof box will remain waterproof even when submerged. So some neat little graph that he produced there. So here's Kent's situation. This is one of the streams Kent is monitoring. This is a tributary to Manor Creek. You can see when the station was put in, all of this cattle access here just upstream of the station. Here's a really good picture of just how dramatic, and this is all just, muddy, exposed dirt, and any storm is just going to flush in there. Kent has, since the time of the installation, Kent has worked with the farmer to fence off the cattle, and get stuff growing in there. I recently visited the station and got some better pictures, but now sadly I couldn't find the summer pictures, but this was nice and lush and really a dramatic change. And even though that particular sensor has had some pretty bad fouling issues, some are worse than others just because of situational dynamics. But you can see here that it does appear that the data are showing the improvements in the stream conditions. So even though depth has increased during some storms over the last several years because of these dramatic storms that are coming through, the turbidity during these storms does seem to have decreased. So Kent not only worked on that location right upstream of the sensor, but a couple other locations further upstream. And so all of that does seem to be showing a difference in the amount of sediment coming into the stream. So that's good signs. And then here's another turbidity example. This is East Stroudsburg University. Paul Wilson is a professor there, and he works in the Delaware River Watershed Initiative. This is just kind of a quick example of a few of Paul's initial stations that he put in. Since this longer standing data was developed, he's put in more stations. You can see he has quite a few on Cherry Creek here. But this is a downstream trend where you can see during storms, the turbidity is worse at the downstream locations as the stream flows through some farmland. And there's a golf course that they're doing restoration work on. That's representing these two. And so hopefully they'll be seeing improvements in this trend over time. This is a bit of an older graph, so there may already be improvements being seen. This is another graph of Paul's work, temperature trends. So going downstream, you're generally seeing increases in temperature. There is one of these sites in here is further downstream, but has cooler temperatures. And I'm guessing that maybe because of limestone influence, but just showing kind of how you can use these stations to kind of investigate longitudinal trends if you put more stations out on one particular stream. So as I mentioned, Paul is a professor, so he also has classes and labs. So he is using these actively in his work with undergraduate and graduate students. He's got an environmental club that he supports and then does work with these in the classroom and has student researchers. One of the Krista Reeves, who's with the Musconetcong Watershed Association now and is a part-time technician for the Stroud Center, was one of Paul's students who got her started on this work. There's Krista there, there's Paul, there's some of his students, there's me, but they get out in the field, they're measuring discharge here with this meter. He gets some people heavily involved doing actual maintenance with the stations, and then has some people even more involved with actual station installations and doing quality control and such. And so he has them involved in research, developing posters and such. And certainly just his intention is to give them real life experience in working in the sciences, as well as, working collaboratively. So another example of use of these stations in classrooms, this is a recent situation in Lancaster County. This is with Conestoga Valley High School. This is Carrie Snavely and Jim Hoven. They have, we've assisted them in putting out 2 stations on Stauffer Run. It's associated with a golf course, and they have already been working with the golf course to bring in native plants and kind of converting some of the grassy areas into meadow. I think they still need to work on some riparian cover down in here, but certainly they're moving towards working with the golf course to make improvements and using these stations in their in their classrooms, getting the kids out to work on these stations and to evaluate data and such.
David, this is Molly. You have about 25 minutes. You're about halfway through.
Okay, wonderful. Thank you, Molly. I appreciate that.
Welcome.
Yeah, and one other thing associated with the whole classroom idea is we are developing lesson plans, and we have a lot of lesson plan ideas documented. They just have to be converted. So if any of the folks involved here would like to just work with data that is already out there, certainly be in touch, because there's opportunities to just, even if you don't put a station out, there's opportunities to work with the data in classrooms. So that is certainly a benefit of the online data portal, Monitor My Watershed, and you don't even have to have a station in order to work with the data. So an example of urban impacts in Westchester, some of the work that's being done by Patty Haug and George Seeds, along with the Stroud Center. There's 5 sites right in Westchester, monitoring streams that are coming out of the town. You can see really contaminated streams across the board. So base flow, looking at about 500 microsiemens per centimeter as the lowest we're seeing in any of these streams. The higher you get in these base flow conductivities, up to one, it's about at 1400, which is 10 times the normal level. These are correlated with land use. So these 2 stations here are these 2 here. So the ones that are draining the most impervious surfaces are the ones that are most contaminated, the most impacted, according to conductivity. Also seeing during winter storms, differences in how these streams are responding to the storms. You can see one here that has a super quick response to storm inflows. And you can see pretty high spikes in conductivity. This is not the max we've seen, but certainly seeing toxic effects from these quick spikes. And then some of these stations, you're seeing long lags in the conductivity elevation. And all this time is going to be much worse for creatures in the stream. We've been supporting a local high school student in doing some of the type of monitoring that the Delaware Nature Conservancy stewards have been doing. So Elizabeth went upstream of the station and monitored at a lot of different road crossings and such, tributaries and such, to see about what was happening and to kind of figure out what the trend was here with regard to inputs. And what she found was that there is a direct correlation between the amount of urban land cover and conductivity. So she delineated sites, watersheds upstream of the station, and shows a pretty tight correlation between % urban land cover and specific conductivity. And then also showing exceedances of chloride and conductivity across the board in a lot of these stations. So conductivity way above these natural levels, and then chloride exceeding toxicity standards from EPA and some other states. Some of these headwater streams are the worst. They're kind of the ones most impacted and coming right out of some heavy urban areas. So seeing pretty much chronic toxic effects there. And so then moving on to a watershed characterization that we worked on with some groups in northern New Jersey. This was a big report that we helped produce with them. The purpose of the report was to inform regional stakeholders of any existing water quality trends that represent a threat to the Pollenskill River and the surrounding community. The recommendations, so we provided recommendations here for a number of different groups, which I'll show. These recommendations should be used to inform decisions and prevent further degradation of water quality. So moving towards this idea of thinking about how to apply the data. And we are currently working on some templates so that this type of characterization can be done more as a standard approach or template that groups can use to understand and apply the data. But some trends we certainly saw, some observations and relationships to thresholds. You can see in this very headwater stream, warm water, unexpected for a headwater stream, expected in a headwater stream heavily developed like this one though, and with lots of sun exposure, long exceedances of trout criteria, referencing regional reference sites. So these are forested sites. Again, this is temperature, but seeing forested, local, smaller forested streams having much lower temperatures than this one. Doing the same thing for conductivity. So conductivity was converted to chloride. And then you can see long periods of time of base flow conductivity and chloride exceeding EPA standards. And then doing the same thing of comparing conductivity to regional reference sites. Again, these are heavily forested reference sites, and you can see conductivity at this headwater Pollenskill stream way above these natural reference sites. They also did some investigation looking upstream of the station and seeing that as the stream flowed through the campus, it increased conductivity the whole way down. So seemingly the campus use of salt and possibly other things contributing to higher conductivity levels. And then they did some longitudinal work and noting that temperature at the headwater section of the Pollenskill is the highest temperature seen anywhere going all the way downstream to lower end of Pollenskill. So showing a real problem with the source of the Pollenskill with regard to temperature. So here's the management recommendations that we made for the Sussex County Community College. I'm not going to go through these, but these are recommendations that were based on the findings that were some of the findings like I just described, recommendations for upstream landowners, recommendations for other local environmental organizations, and then recommendations for the town of Newton municipal officials. And then just to finish off this section of the presentation, this is some work that we've done internally at the Stroud Center, but just showing some of these basic trends across the Delaware River Basin, kind of similar to what Elizabeth showed in the local watershed, but showing that with percent forest, as forest goes up, temperature goes down. And this was Mark Paypock at the Stroud Center, just sort of making a general implication here of with 10% forest, you get about a half a degree decrease in temperature. And then trends like this, where you're seeing turbidity during storms, kind of like the trend that we saw with Kent's data, turbidity going down as natural land use, forest and wetland goes up. So just in summary of this example usage of these stations, each parameter, as you could tell with those examples, each parameter has different implications for the ecology and how what that means for management of the watershed. So when you're working with these stations, you certainly want to understand the variables that you're looking at and how each of those may or may not suit your specific purposes for the station. There's a wide variety of uses, and so you just want to, before you start working with one of these, you want to be clear on what your purpose is with the stations, and certainly thinking about your audience and what types of information, what types of data, what types of analyses and management recommendations are going to be useful to certain audiences. And that also applies to classroom work, certainly thinking about what's going to be most interesting and useful for students to understand. So a main consideration here is what's your action? What are you going to be doing? How will your data be used? How are you going to interpret it? How will the data that you're producing help you work towards your ultimate goal of having a station? So to that end, simply, you want to do your best to have specific goals already laid out before you work with one of these stations, and have your plan articulated before you're monitoring. What if the data shows this? What does it mean? If the data shows this, what does it mean? Okay, so on to station management. Okay, so we're shifting here. Now we're stepping away from how these stations are used, and we're going towards just the logistics of how to maintain a station, how to ensure that it's collecting good data, how to troubleshoot and figure out if the data are indeed good. And I mentioned troubleshooting. Hopefully I'll get to a little bit about some kind of main ways that we troubleshoot problems with these stations. Okay, so pointing out here, this is a sort of a Delaware specific thing, but a lot of the materials are applicable to anyone. So there's a lot of good resources here. This tab here, help resources, is very good. All of the meetings and workshops that we do, a lot of them have been recorded, so you can access that information here. One of the guidance documents we have in this help section of this webpage is this recommended roles and responsibilities for managing a station. So within that, there are 4 roles basically: for the role of a station owner or manager, a role of monitor my watershed, so paying attention to the data portal and what's going on there, and then doing maintenance, and then doing quality control. And this is detailed. I'll have this summarized a little bit better in a couple slides. But one point to make here is that Cheryl's a good example of this. She downplayed her expertise, but she really has developed some real skills with this process. And it's good to have at least one person when you're working with these stations who's going to be able to kind of take on a technical lead type role, just to kind of keep things in front of you. One thing to point out here is simply that Monitor My Watershed you need to involve the usage of Monitor My Watershed in each of these steps. So it's important to be consulting the data on a regular basis, regardless of what role you're playing. Whether you're a station owner, you need to be checking Monitor My Watershed. Whether you're monitoring Monitor My Watershed, of course, you're going to check that. But even when you're cleaning the sensors, you want to check it before and after you clean the sensors to see what's happened. And you want to see what the data look like while you're out there and doing your work. Same with quality control. You're going to be checking the data on Monitor My Watershed to see if your cross checks match up. And I'll get into that in more detail. So management and oversight by the station owner, making sure that all 3 of these other roles are performed as they need to be done. Desktop monitoring, that's just checking Monitor My Watershed on a daily basis, is the recommended. Certainly you don't have to do it every day, but it's recommended that you really regularly keep track of the station, because if it goes wrong and you haven't checked it in several weeks, you may have lost weeks of data or even months of data. Maintenance, we're recommending once a week to clean the sensors. That is, again, situational. It's really dependent on the site. But as a standard, we recommend once a week until you really understand the station enough to know how frequently you need to go for your particular situation. And then quality control, recommended to do quarterly. But again, that can be done situationally according to what you're seeing with the data. If you see some wacky data, you can go out and check it to make sure. So in your planning, certainly each of these tasks takes time. So you want to make sure that you have the people involved who can allocate the amount of time that's necessary. So desktop monitoring, some basic functions of this. You're going to go to Monitor My Watershed, where you get this map and you can check whether the station is live or not. So dark green is good. That means your station is live and is transmitting data as it should be. Light green means that there may be some kind of outage. Sometimes these stations don't transmit every time. So if you get sort of a downtime with the cell coverage for whatever reason, you can get this. And then you get darker and darker into red. And that's just going to tell you there's something wrong with your data transmission. Either the cell board is broken, or the cell tower is down, or any number of other things. Another component of desktop monitoring, keeping track of Monitor My Watershed, that is to check the data panels or sparkline plots. These give you the these give you the current readings, so you can check the most recent readings, and you can tell if the numbers are out of range. So here, battery voltage of 4 looks good. 3.5 is kind of your point where things start cutting off. 3,000 millimeters, over 3,000 millimeters, that seems suspicious. This type of pattern also looks pretty suspicious. So, tuning into what the data should be so that you can key into things like this and identify if your station is having problems is definitely a good process to do on a daily basis. We also get obvious signals and these spark lines, such as this -9999 signal, which means that there's not a good communication between the mayfly and the sensor. It could be a problem with the wire. It could be a disconnected wire. It could be a problem with the mayfly board. But this is certainly a signal you want to keep an eye out for when you're monitoring Monitor My Watershed. And then you can also check the time series to look at data patterns and see what's going on. We have this pattern that often shows up with depth and temperature being directly correlated. That indicates that the CTD sensor has gone bad. So these kind of just red flags. Another thing to keep in mind with just checking in on Monitor My Watershed, again, noting that this is your real-time feed and kind of matching this up with current time, making sure that you're transmitting correctly. But also, I wanted to make sure to point out that taking your smartphone out to visit a site is definitely a process that you're going to want to get in the habit of, as long as you have cell coverage, because you can check these sparkline plots. It's harder to look in the TSA on your phone, but these sparkline plots show up really nice on your smartphone, and you can just be there and check back and forth between what the station is reading and what you may be reading on your handheld meter, or what you're checking if your sensor cleaning worked, and so on. So getting into maintenance and cleaning of the sensors, as I just mentioned, checking these real-time plots to before you clean, and then checking them after to see if your cleaning changed anything. Certainly if there's some obvious fouling going on with sensors, you want to check that your cleaning addressed the issue, and doing that via your smartphone and checking these plots. As far as the actual, excuse me, as far as the actual maintenance process, the main job here is cleaning the sensor with a brush. So using these long, softer white bristles to clear all of this debris off, making it look like this, clearing the external part of the sensor. And then often it can be necessary to actually get those long bristles into this slot to clean these screw heads. These are where the conductivity is measured, and those can get algae growing on them. They can get fine particles on them. And it's important to get those bristles in there to clean those. One other thing to mention here, I didn't, George is going to talk about this as well, but you can get particles, bigger particles that get wedged in there and then affect the pressure transducer. So at those times, it can be important to take the whole bundle out of the stream and look, and George will get into some of those types of details. Also cleaning around the logger box. So you can get a lot of vegetation growing up around these boxes and starting to cover solar panels. You also get ants and stuff that can kind of start creeping in around here. And if you have vegetation up here and you open this box and try to close it and you get any sort of stick or even a small piece of grass in the seam, you know, in this door, it can allow water in, and that's not good for electronics. So you want to clear all this debris out from around a logger. So moving on to quality control. And Molly, feel free to chime in if you would when I'm at five minutes or so.
You are at 5 minutes or so.
I'm at 5 minutes or so. Okay, so I'm probably not going to get to troubleshooting. Main point here with quality control is essentially you're just going out with a calibrated meter and checking to make sure that the station readings are close to your calibrated meter. So you're checking this number against this number. With the depth, you're going to take a ruler and simply measure from the pressure transducer, which is located about right here, up to the surface of the water and compare it to the depth here. SD card, I mentioned this before, but that's another quality control process that we recommend downloading the data on a quarterly basis, just to make sure that you've got the most secure data actually secured in your possession. So just a little bit on troubleshooting here. Here's the 4 most common problems. Station is offline, fouling or sensor malfunction, this -999 signal, and battery voltage levels, power levels. So common problems with power, 3.5 is a cutoff, so you want to keep an eye out for that. That will stop your cell transmission. You want to make sure your cell plan is paid. That will also cause your station to stop sending data. These boards can go bad, so you want to make sure that that is not an issue. Monitor My Watershed also can have issues. So every now and again, there'll be sort of a period of time when monitor will be down and stations will show up as not transmitting. And then there can be cell tower issues as well. So fouling can certainly happen with sensor burial. You can have growth on these turbidity sensors. You can have all kinds of debris and stick fouling of the sensors in general. All of that can cause bad data readings. Sensor malfunction issues, certainly patterns like this, these strange correlations that I mentioned, negative numbers are obviously going to be a red flag for station malfunction or sensor malfunction. And then this -999 signal, which means there's a communication problem between the mayfly and the sensor. That can be due to a bad jack where the sensor hooks into the mayfly. It can be due to a bad connection with the actual board. You can have chewing of wires, as I mentioned yesterday, of animal vandals. And then you can actually just have bad sensors that just come bad from the company, or they just go bad for whatever reason. And then battery voltage, certainly solar charging can be an issue. Snow, or I mentioned vegetation, or a lot of canopy coverage can affect charging. You can have batteries that go bad. If you get a little water in your box, you can have corrosion of the batteries, and you can have chewing of wires again. Or this is a situation where a storm ripped this out and damaged the wire here of the solar panel. To support battery issues, you can get these these charging setups where you can have a backup battery and go and swap batteries. So just to conclude here, we have a lot of different materials, data sheets here available to use with these stations, a manual, there's quick guides, a maintenance quick guide, a quality control quick guide. There's supply lists that you can use to support maintenance and upkeep. And there's lots of different videos that support maintenance and upkeep of these stations. And as I mentioned, there's lots of workshops and conferences that have been recorded. Our monthly meetings, we have a Delaware Basin EnviroDIY monthly meeting every month, which any of you folks would be welcome to attend. Just be in touch with me if you'd like information on that. I can include you on the email distribution list. And then just as a summary for today, be clear on your purpose, your goals, and your plans for the data. So before you put a station out, make sure to take the time to consult with yourself and others about how you're going to use the station, how you're going to use the data, how the data will inform any decision making that you want to make or help other people make. Good data require good maintenance. So in order to keep the stations functioning well, you have to actually pay attention to them. You have to go out to the station. You have to do things like quality control and paying attention to monitor my watershed. Volunteers are super helpful. This is not a 1 hour a month type thing. This is multiple hours per month to maintain one of these stations. There are plenty of guidance materials to support all of this type of stuff. And just to end with, collecting the data is one part, but there's also just, what do you do with the data once you've got it? So this idea of analysis, interpretation, and communication, you definitely want to think about that and just be clear before you work with one of these stations as to how you're going to use it in a purposeful way that you set yourself. Okay, so that's it. That's our contact information. I'm Dave. Shannon Hicks, as I mentioned yesterday, is the designer, the engineer of the Mayfly, of these standard stations. Rachel is a technician. Krista Reeves is a technician. Carol and George are master watershed stewards who have done a tremendous job over the years supporting efforts and engaging other master watershed stewards. So I hope I didn't go too much over there, but I think we can go on to George at this point.
Thank you so much, David. Our next presenter is George Sees. As David mentioned, George is a master watershed steward for Chester County. And George, please begin whenever you are ready.
Okay, thank you. And I'm going to share my screen here. Okay, there we go. Great. So, I am going to, well, as Molly and David said, I'm a volunteer Penn State Extension Master Watershed Steward in Chester County, and I am involved in managing and maintaining 2 of the 5 Westchester stations that David discussed. And what I'm going to do is really just try to give you some, to go over 2 or 3 case studies that just show you from a practical standpoint some of the issues that you are going to encounter when maintaining stations, and the objectives really for my little piece here is to illustrate the situational dynamics of managing an EnviroDIY monitoring station. As David explained, every situation is different, and you need to become familiar with the situation at each individual station and stream. And you begin to gain that familiarity as you are involved with the station. And then also to illustrate the importance of consistent monitoring and regular maintenance site visits. I don't think we can emphasize that enough, because obviously if you are not maintaining your station, you are more likely to have bad data, and that defeats the purpose of your project. These are the 2 stations that I'm responsible for, Taylor Run and Black Horse Run. These 2 stations are on urban suburban streams, pardon the typo there, urban suburban streams with longstanding and recent development. On Taylor, there has been some massive recent development just over the past year, which we have seen the effects of on the stream, and exacerbate the high flashy flows that we're seeing more of in recent storms. Kinds of things that can happen as a result of these flashy flows, particularly in urban and suburban streams, is they can tear out and damage loggers, which we will show you some examples of in subsequent slides. They can carry objects downstream that damage sensors, boulders, logs, loggers, churn up sediments, which can foul or damage sensors, and it can also carry more nutrients. We see this in the summer in particular, that algae contaminates the sensors. The first scenario here, little case study, was Hurricane Ida during on August 18th and 19th. The sensor site, as I mentioned, is a Taylor Run upstream of Westchester wastewater treatment plant. And the depth at the base flow in the stream is typically about 375 to 400 millimeters at that time. Actually, since then, it's actually increased because the channel has deepened considerably just since these storms this summer. But at that time, the base flow was 375 to 400 millimeters. We had about 4.5 inches of rain on the night of August 18th and early morning of August 19th. And I noticed that morning, as David described, one of the things that is important to do is to check the data on Monitor My Watershed on a daily basis. I noticed that the sensor depth had increased as I expected that it would, but it increased from the base flow of around 425 at midnight to 7,692 millimeters at 1:50 a.m. in just about 2 hours. I knew from just my familiarity with the data that depth level of 7,600 millimeters was about 3 times higher than any previous post-storm depth measurement. I knew it had rained a lot, but seeing a depth measurement of that magnitude was more than what I it should have been. So I confirmed using the time series analyst function on Master My Watershed that it indeed was apparently an incorrect, an errant measurement, because this measurement was actually it was about triple the previous highest measurement, which occurred on 8/4 of 2020, in which we actually received more rain, which is 5 inches. So you can see here on the time series analyst, and this is where it is helpful to learn how to use the time series analyst, that the previous high maximum depths were a little over 2,000 millimeters, and this was with 5 inches of rain. Here we only had 4.5 inches of rain, and we're up about 3 times that. So something seemed to be wrong. This actually just illustrates the watershed of Taylor Run. You can see that this area right in here is the area of development that has just recently occurred in the past year or two, which has increased the dramatic changes in the stream bottom and has made station maintenance even more involved and more critical. Here you can see, this doesn't really, it's kind of hard to see here, but you can actually see here at where the sensor is located. You can actually see the bottom here, the gravel in the bottom. A year later, it's in this picture here. It's kind of hard to see the bottom. The channel has deepened considerably, and as a result, makes maintenance more challenging. So anyway, back to this particular situation. After noticing that the depth was unusually high, I visited the sensor to clean the sensor and clear any debris that might have been fouling the sensor, causing exceedingly high depth measurement. The assumption was that there was a pebble or something lodged in the sensor that was causing excessive pressure on the ceramic depth sensor disc. Even though the stream had receded to within its banks at that point, it was too deep for me to get in the stream to inspect and thoroughly clean the sensor. But I was able to reach down and clean it the best I could from the bank. But that cleaning had no effect on the errant depth measurement. There you can see that was when I went to clean the sensor after the storm. I was unable to get in it at that point. Finally, after the stream level had receded further and I was able to get in the stream, I was able to remove the sensor bundle. And here you can see a picture of the pebble that was lodged in the sensor. And this is the kind of stuff that you encounter during these flashy storms, which really requires and illustrates the need to, get out there. Even though your sensor is transmitting, you need to get out there and actually physically inspect the sensor, because this is the kind of thing that can happen. You can see here from the time series analyst data that the depth was up here over 7,000. I cleaned it, and you can see how it immediately, after I dislodged the pebble, it immediately dropped down to normal levels. Okay, scenario number 2, also on Taylor. Again, after 7 inches of rain on September 1st, the depth of measurement again rose to well over 7,800 millimeters, which I knew again was a false reading. Visited the station again. It was, and found that the entire station has been ripped out and laying on the bank with a solar panel dangling, although still connected. The water was still too deep for me to get in at that point. But since the station had been entirely dislodged, I sought the assistance of David and the Stroud team, and they went out to do some stopgap repairs. But again, here, one of the key lessons is that if the station, even if the station is transmitting, there's no substitute for visiting the site in person after a significant storm to inspect the site conditions and any potential station damage. Here again, you can see how the depth, increased to a very abnormal level as soon as it was cleaned and another pebble dislodged. It went back down to normal levels. But here you can see some pictures from that storm. The entire logger and pole laying alongside of the stream. The dangling solar panel. But even though it was ripped out, it was still transmitting. So the Stroud team did some quick fix, or David did some quick fixes to allow it to continue to transmit until more complete fixes could be made by one of the Stroud technicians. It was just set back up and the solar panel reattached. But again, the point here being that there's no substitute for physically visiting the sensor site. The scenario 3, Black Horse Run Station. This station frequently gets buried in sediment after a storm, resulting in inaccurate measurements. And over the past year or so, it seems that every time we get a significant rain, the sediment around that sensor buries the sensor, and you see the conductivity level drop to an abnormally low level. The normal level is around 600 ultrasiemens per centimeter. And when you see it drop and stay down and doesn't recover after a storm, you can bet that the sensor is buried. You can see here how these are 3 situations where depth increases, the conductivity drops, stays down, looks really funky. I go out to unbury the sensor, and it immediately goes back up to normal levels. Goes along here at relatively normal levels. We have an increase in depth after a storm. The conductivity plummets, stays down until I go out and unbury the sensor, and again it bumps right up. And the same thing happening here. Storm, depth increases, conductivity goes down, sensor buries, stays down until you unbury it, which is why it's very important to monitor the data on a routine basis, particularly after storms. So again, this just illustrates, this is a picture of the Black Horse Run watershed, and we've seen, as I said, bigger storms recently have meant that sensor burial happens almost every time. Again, here, these are just pictures of this sensor, and you can see, you can actually see, this really doesn't illustrate it as well as it could, but this is what it looks like currently. Here's some examples of why we see so much sediment. This is just upstream from the sensor, these big washouts along the bank. The key takeaways here: regular monitoring of the data along with maintenance and QC site visits are required to ensure, sorry about that, and to ensure collection of accurate data and to gain familiarity over time with data patterns and stream and bank conditions. Adequate staff time or committed volunteer resources are vital. As David said, people really need to be committed, and there has to be sufficient time to actually get out there on the stream routinely. And I want to put in a plug here for the Penn State Extension Master Watershed Steward volunteers. We are an excellent resource to help support your EnviroDIY stations. And they exist in many counties throughout the state. I've included a link here to the Master Watershed Steward County programs on this Penn State website. And these are all the counties in which Master Watershed Steward programs exist. So you can go on the website, find out who the contact person is, and see if you can recruit some volunteers to help you with your stations. So that's all I have. Be happy to take any questions if there's time.